Hello and welcome to my electromagnetic waves presentation. Everything you've learned in our electricity and magnetism course culminates in the topics we'll discuss here. Now you have the background information to understand and apply this theory. Congratulations. The goal of this presentation is to establish simple equations governing 3D motion, construction, energy, and speed of electromagnetic waves, and to understand how they travel through a vacuum like space. Some examples of electromagnetic waves are visible light, infrared, ultraviolet light, microwaves, X-rays, radio waves, cell phone signals, and much more. Some of the tools we will use include the following. The Maxwell Equations. You may not have heard this term before, but you've seen the 4 Maxwell equations under different names earlier in the course. We will discuss this in the next few slides. The second thing is the equation of a transverse wave, which we talked about last class. This is a wave that oscillates in a direction that is perpendicular to its velocity through space. Think of a snake winding as it moves along the ground as a visual. And the third thing is the equations for energy stored in a magnetic field and in an electric field, along with the concept of energy density that we'll discuss in this presentation. The person responsible for these 4 equations is James Clerk Maxwell. The Maxwell equations consist of 4 equations which you've seen in class already. We've got 2 Gauss's law equations, Ampere's law, and Faraday's law. Maxwell also modified Ampere's law in a very important way, which we'll see in a minute. But let's talk about these 4 equations first. Gauss's law for electric fields states that the electric flux through a closed surface, real or imaginary, is equal to the charge enclosed by that surface divided by the constant epsilon sub 0. We've got Gauss's law for magnetism that states that the net magnetic flux through any closed surface must always equal 0. So this is a mathematical representation of the statement that no one has ever observed a magnetic monopole in nature. In other words, every magnetic field line that leaves a magnetic source from the North Pole has to return to it to the South Pole. Then we've got Faraday's law of electromagnetic induction, and we've seen this in class as if a magnetic flux changes through the area bounded by a wire, then an induced EMF will be generated around the perimeter of the wire. That EMF will counteract the change in magnetic flux. Well, the Maxwell version of Faraday's law shown here is slightly different. It contains the closed integral of E dot dl. This term was something that we discussed when we first defined the electric potential, so it should be familiar. And the way that I framed it was a work is equal to force times distance per unit charge in this case, so E dot dl is that force times distance per unit charge. So this is a representation of work essentially around a closed path. We'll talk about this rewritten Faraday's law in a few slides. And then Ampere's law, as we've discussed it so far, states that if we have a surface through which current passes, there will be a magnetic field along the path bounding that surface. However, we'll see in the next slide that this equation requires an additional term to account for changing electric fields where current does not necessarily flow through the bounded surface. This will make more sense in the next slide. As you can see, the 2 surfaces shown here share the same bounding path. The surfaces in question are the disc-shaped surface on the left and the dome-shaped surface on the right. Conventional current, labeled I sub c, flows through the left-hand surface. So, according to Ampere's law, there must be a magnetic field on the bounding path. But the dome-shaped surface does not have current flowing through it. So, the path should have no magnetic field, and hence a discrepancy exists here. Maxwell's solution was to observe that there's a changing electric field through the dome-shaped surface. So he described the notion of a displacement current, i.e. a changing electric field that also generates the magnetic field. So in order to define displacement current, or virtual current due to a changing electric field as it is, we take a look at these capacitor plates. And we recall that the equation for current is dq dt, and Q for the capacitor is given by capacitance times voltage. Now recall that voltage across the plates is given by electric field times D, where D is the separation distance between the plates. Recall also that the capacitance for a parallel plate capacitor is epsilon sub 0 A over D, where A is the cross-sectional area of each plate. So when we plug everything in and simplify, we get an equation that relates current, called displacement current, to the changing electric field. So adding this term to Ampere's law, Maxwell completed the equation. Up until now, our form of Faraday's law has had induced EMF on the left-hand side, changing magnetic flux on the right-hand side. Recall that when we define the electric potential, we said that delta V is equal to the integral from A to B of E dot dl. So this is a statement of work per unit charge is equal to force times distance per unit charge. And so, since the electric force is a conservative one, the work done by it is conservative also. And so if we integrate around a closed path, we're returning to our original position. The net work done should equal 0. But now we look at induced EMF. So this induced EMF is not conservative. So E dot dl does not equal 0 on a closed path. Instead, it equals the change in magnetic flux that's causing it. Now let's look at the basic idea behind an antenna and how it produces electromagnetic waves. So if we have an AC source as shown attached to an antenna, current's going to flow up and down along the antenna, so there's going to be an alternating electric field as shown. And since current's flowing, there will be also an alternating magnetic field circling the antenna as shown. The energy from these two fields leaves the antenna and travels outward in all directions. This is called near-field radiation. At a long distance from the antenna, the energy will tend to straighten, giving rise to plane waves. So we have transverse waves with the electric field and magnetic field at 90-degree angles to each other and to the direction of the wave's velocity. Our assumptions for the remainder of this derivation are as follows. A, we have plane waves. B, the wave velocity is along the x-axis. The electric field oscillates along the y-axis, and the magnetic field oscillates along the z-axis. And so we assume an empty vacuum where no current or charge sources exist. And so the Maxwell equations look like this. So in this derivation, we're only going to use the bottom two Maxwell equations, the transverse wave equation, and two energy density equations that I'm going to discuss later. Here we apply what we know about transverse waves. We have two waves here, the electric field wave and the magnetic field wave, both traveling in phase with one another. So the variables E naught and B naught are the electric and the magnetic field amplitudes, respectively. All of the other transverse wave values apply. We can calculate a wave number, k, a frequency f, and a wavelength omega, etc. Let's remind ourselves of what our goal is, to develop equations of motion for the electromagnetic waves. So here we're going to look at Faraday's law and how it applies to a zoomed-in section of the wave. So we're going to rewrite the left and right sides of Faraday's law using simple geometry from the figure that's on the left. So on the left-hand side of Faraday's law, using the graphic, we're going to integrate E dot dl around the entire rectangle shown in black in the pink portion of the wave. And so the left-hand side, we're calling the length of that vector E. And so E dot dl is equal to E times the height delta y. On the right-hand side, we have an additional height called dE, because that vector is slightly taller. And so what we have on the right-hand side is E plus dE delta y. And notice on the left-hand side, E goes against the integration path. And so it's negative E delta y. And so the whole thing simplifies to dE delta y, and then we're finished with the left-hand side of the equation. Now let's look at the right-hand side of the equation. We see that in order to calculate magnetic flux rate of change, we use area, which is delta y times dx, multiplied by the magnetic field rate of change, dB dt. Now we equate the two sides and notice that we can cancel the delta y from each side. Also, we will divide by dx on both sides to get our usable equation. So now we're going to use the same logic as we did on the E dot dl slide, and we're going to take B dot dl. And note that if on the left we have B, then on the right we have B plus some small amount of additional height, dB. And the top and bottom once again do not contribute. And notice this time the taller side goes against the integration path. So the result is B delta Z minus B plus dB times delta Z. And this whole thing simplifies to negative dB delta Z. Now, if we solve the right-hand side, we take the rate change of flux to be area dx times delta Z multiplied by the rate change of the electric field. The mu sub 0 and the epsilon sub 0 come along for the ride to give the equation shown. Now if we equate the two sides, shown on the bottom here, and then we simplify and divide through by dx once again, we get our second usable equation. Now we're about to have about as much fun as you can have in physics. So we have these two equations that were derived from Maxwell's equations, and we're going to apply them to the transverse wave equations for the electric field and the magnetic field. And so in order to do that, we need to take partial derivatives. This is a calculus 3 topic, and I don't want you to worry too much about it, but I'm going to go through an example, and it should make sense. So when we have an equation in terms of two or more variables, we take the partial derivative by ignoring all the other variables and treating them as constants. So for instance, if I take the partial derivative of E with respect to x, I'm going to treat time as a constant. And so using the chain rule, we have negative E times k, which comes from the inside of the cosine term, times sine kx minus omega t. So the negative sine kx minus omega t comes from the cosine term. And notice we don't have an omega because omega is the coefficient of a constant in this case. So now let's take partial derivatives of the remaining three equations. And so those are shown here. And what we're going to do is we're going to take these results and plug them into the top left two equations here. And we're going to see that all of the sine kx minus omega t's will cancel, and we'll get a really nice result. So all of our hard work paid off, and now we have the two equations highlighted by the box here. And they're really simple, straightforward equations. Now we can use transverse wave equation properties to simplify these two equations that we've developed. So the first equation is really easy. We divide E sub 0 by B sub 0, and we notice that that's going to equal omega over k. So if we look at our transverse wave equation relationships, omega over k equals the speed of the wave. So that gives us equation 1, which I've highlighted in a green box here. Now let's look at the bottom equation. So this one's also pretty simple. We're going to divide E sub 0 by B sub 0, and you can kind of see where we're going here. We're going to equate it with equation 1 when we're done. And so if we divide this is what we get. So dividing through and simplifying, we see that E sub 0 over B sub 0 from equation 2 gives us 1 over the speed of the wave multiplied by the constants 1 over mu sub 0 epsilon sub 0. And now if we set these two equations equal to one another and we simplify, then we get a compact, nice representation of the speed of an electromagnetic wave in a vacuum. And that speed is equal to the square root of 1 over mu sub 0 epsilon sub 0. So these are the constants, the electric permittivity and the magnetic permeability. We've used them in class multiple times. We can solve for this speed, and it turns out that the speed is called the speed of light, and that all electromagnetic waves travel in a vacuum at that same speed. And solving for the speed of light gives a value of 3 times 10 to the 8 meters per second. And there's one other relationship about these electromagnetic waves, and that is that the speed, the wavelength, and the frequency are all interrelated. So we can only have one frequency associated with a particular wavelength and vice versa. All right, now we need to talk about how much energy is carried by these electromagnetic waves. And so we're going to start out with a parallel plate capacitor. So we know that the capacitance is epsilon sub 0 A over D, and we know that the voltage is E times D. Keep in mind D is the separation distance of the plates, A is the cross-sectional area of the plates. And we know the equation for storage for the capacitor, which is energy stored is equal to 1/2 CV squared. So plugging in for C and V and simplifying, we see that we've got A times D multiplied by 1/2 epsilon sub 0 E squared. But what is A times D? A times D is the volume that the capacitor occupies. And so it's the volume that the electric field occupies. And so if we want energy per unit volume, we simply divide out the AD, and we're left with energy density for the electric field is 1/2 epsilon sub 0 E squared. So that's one important equation. Now let's look at the solenoid. So we've done example problems in class where we derived the magnetic field surrounding a solenoid, and we've derived the inductance, the self-inductance of the solenoid. So if we plug in the U is equal to 1/2 Li squared equation, which is the energy stored by the solenoid, we've seen that too, and we plug in for L there, and then we solve the magnetic field equation for current, square it, and plug that in. Once we simplify everything, we get the equation shown, which is A times L, which is the cross-sectional area times the length of the solenoid, times 1/2 B squared over mu sub 0. But A times L is the volume that the magnetic field is going to be in, and so to get the energy density, we just divide out that AL, and we're left with the equations shown here. So these are the two important equations for energy storage. They're energy densities. So we've already seen that we have an expression for the peak amplitudes of the electric and magnetic fields, E sub 0 divided by B sub 0. And we also know that the electric and magnetic fields are in phase with one another, which means that E sub 0 divided by B sub 0 is equal to E divided by B everywhere along the wave. And so we're going to take advantage of that fact here. And so you see I solved for B squared in terms of E squared by taking that ratio. And now what we're doing is we're adding the energies between the two fields. And one interesting thing we see is that if we sum the two energies, we get twice the electric field energy. So what does that mean? It means that the energy in the magnetic field equals the energy in the electric field at all points. We could do the same thing and get the energy in terms of the magnetic field squared. So I'll leave that as an exercise for you to do if you're interested. And now, so we can ask questions like how much energy would pass through my cell phone a certain distance away from, say, a 5G tower. And to do that, if we know the energy densities of the wave, the electric field and the magnetic field, we could calculate the volume of the cell phone as follows. It would be the cross-sectional area of the cell phone multiplied by the speed of the wave times dt, which is the amount of time that's elapsed. So in dt amount of time, c times dt multiplied by the area would give you the volume of the energy. And then multiplying that by energy density gives you total energy that it passed through the cell phone in that amount of time, du. And that small volume Ca dt contains the energy. And now what we can do is we can divide through by the dt, and that gives us units of power, or watts, and then divide through by the cross-sectional area, and that gives us watts per meter squared. And that would be a typical value used in engineering when it comes to analyzing electromagnetic waves and designing towers and things like that, would be watts per meter squared produced. And now if we split out one of the electric fields in the E squared, and note that it equals the speed of light times b from a previous equation, we find that the power per unit area is simply E times b divided by mu sub 0. What a simple equation. And the power per unit area is carried in the direction of the wave, so we can call it a vector. And that vector is called the pointing vector. Finally, we need to talk about the different types of electromagnetic waves. And so we see here the range of visible light is just a narrow band. And right below red, we have infrared. Right above violet, we have ultraviolet. And so these are the associated frequencies and wavelengths. We can see gamma rays, radio frequencies, microwaves, cell phone waves would fall somewhere in there. And you could easily look up the frequencies and the wavelengths for any type that you're interested in. So hopefully you enjoyed the presentation.